So, questions like we looked at on Friday, they were already basically set up in the format that we're used to working with when it comes to talking about transformations, right? So that was fairly straightforward once we saw a couple examples on how those were done. Because they are set up in that format, a times f at x minus h, or b bracket x minus h plus k. Okay, so that was fairly straightforward. But what about when we see something like this, where it's not set up in that format? This is still a transformation of y equals 1 over x. Because you can see you've got that denominator on the bottom of x minus 2, but there's also an x on top. Right? So it's completely different. So it says identify any asymptotes as well as the intercept. So we could start with those. There is a non-permissive value here for x, and that is that x cannot equal positive 2. Because if x equals positive 2, you're going to get a denominator of 0. And that's a problem, right? So we know that x cannot equal positive 2. So we have a vertical asymptote at x equals 2. So we can put that in there. Bless you. All right, we can see if there are any intercepts here. Remember, the x-intercept is always where y equals 0. So we can take the equation and let y equal 0 and solve for x. You get this, Jason? Good. So we have a rational function, 4x minus 5 over x minus 2. We want to know when that equals 0. A rational function will equal 0 when the top equals 0, because 0 divided by anything will equal 0. A rational function will equal 0 if the top equals 0. So this rational function equals 0 where the top equals 0, where the numerator equals 0, where 4x minus 5 equals 0. So we can add the 5 to both sides and divide by 4. And there is our x-intercept. It is at the point 5/4, comma 0. So we can put that on our graph. 5/4 is 1 and 1/4. So approximately right there. Right? We can find our y-intercept. Our y-intercept is always where x equals 0. And I've said this before, that on almost every diploma exam, there's a question where they ask you to find an intercept for some function. Could be a rational, but it could be an exponential. It could be a logarithmic. Who knows? They're usually on there, though, and they're always done the same way, no matter what the function is. The y-intercept is where x is 0. The x-intercept is where y equals 0. So in this case, we want to find the y-intercept by letting x equals 0 in the equation. So 4 times 0 is 0. Take away 5 is negative 5 over 0 take away 2 is negative 2. And negative 5 divided by negative 2 is positive 2.5. That is our y-intercept. That is where x equals 0. So that is a point 0, comma 2.5. So that is approximately right there. That's all we know right now. Obviously, that's not enough to go on in order to draw this graph. All of the rational functions that we did before had a vertical asymptote, but it also had a horizontal asymptote. Originally, it was the x-axis, and sometimes that shifted up and down. So we can assume that this graph will also have a horizontal asymptote. But where is it? How do we find it? Let's turn to our graphing calculator. Let's put the equation in our calculator. So I'll use brackets to keep the numerator and denominator together. So 4x minus 5 in brackets is the numerator, divided by x minus 2 in brackets for our denominator. So zoom 6 to make sure my windows are still their standard settings, and that's what it looks like. Okay. Even though the calculator doesn't show the vertical asymptote, we can see where it is. If we go into our trace mode, notice it goes by default normally to where x is 0, and it gives us our y value of 2.5, which we found algebraically, the y-intercept. We can also check to make sure we got the correct x-intercept. The x-intercept we found to be 5/4 or 1.25. So if I put that in, that's confirmed because y does equal 0 there. We said that our vertical asymptote was at x equals 2 because that's the non-permissive value from the denominator. If I try and see what happens when x equals 2, I don't get a value for y returned because x equals 2 is a non-permissive value. That is where that vertical asymptote is. But we can also see by looking at this graph that there is a horizontal asymptote. It looks like it's obviously above the x-axis. The value of y is positive there. If I go into the trace mode and let's let x equal, let's say 8, which takes us over to the right, look and see what the value of y is, 4.5. And what happens if we use our arrow key and move over? As x gets larger and larger, look and see what's happening to the value of y. It is getting smaller and smaller. It's approaching a value of positive 4. And we could keep doing this till this time tomorrow, and it would never get to positive 4. It's getting closer and closer to positive 4, but it'll never get there because that is actually the equation of the horizontal asymptote. So, from the graphing calculator, remember the GDC, graphic display calculator, the horizontal asymptote is at y equals positive 4. That's our horizontal asymptote. And if you look at the original equation, I want to point out that the degree of the top and bottom is the same. They're both first degree polynomials on the top and the bottom. They're both x's to the power 1. And if you take the coefficients of the x's, which are positive 4 on the top, positive 1 on the bottom, and you divide them, 4 divided by 1, you actually get 4. And this is actually how you can get where that horizontal asymptote is. We just saw what it was. It's y equals 4. We saw that on the graphing calculator. But how do you determine that? Well, this is how. If the degree of the top and bottom are the same, divide those coefficients, and that'll tell you where the horizontal asymptote is. In this case, it is a line y equals positive 4. So that's this one right here. And again, if we look at our calculator and put our windows back, whoops, I'll go zoom 6. Try that again. Zoom 6. We see once again that this graph has two arms to it, one in the bottom left quadrant, the other in the top right quadrant. We already have our x and y intercept, which is part of the bottom left quadrant. As well, we know where those asymptotes are and what happens as the graph gets closer and closer to it. So that's that part of it. We also want to have kind of some idea of what the other piece of the graph looks like in the top right-hand quadrant. So if we wanted to, we could just find a couple points by choosing any values of x that are greater than 2, because the line x equals 2 is our vertical asymptote. So to the right of that, the values of x are larger than 2. So if we find out what happens when x equals 3, so using function notation, let's say what f at 3 is. 4 times 3 is 12. Take away 5 over 3 minus 2. So that'll be 7 over 1, or 7. So the point 3 comma 7 is part of this graph. 5, 6, 7 will be up there somewhere. And if we found one other point, let's say when x is 4, f at 4, 4 times 4 is 16, take away 5 over 4 minus 2. So that'll be 11 over 2, or 5.5. So that is the point 4 comma 5.5. So that is approximately right there. So this just gives us a couple points of reference for that portion of the graph. It just gives us a more accurate sketch. If we were asked to state the domain and range of this, we could write our domain as all values of x such that x cannot equal positive 2, but otherwise all real numbers. Our range, all values of y such that y cannot equal positive 4. So there's our domain and range. They come directly from the asymptotes. The asymptotes provide us with the only restrictions on these graphs. Okay? So the one on the next page is very similar. We're asked to graph this, identify asymptotes and intercepts. So our vertical asymptote comes from the non-permissive value. We have a denominator of x minus 4, so x cannot equal positive 4. So our vertical asymptote is at x equals 4. And now we can see, or we just saw, that we can get the horizontal asymptote. As long as the degree of the top and bottom are the same, and they are, they're both x to the 1s, the horizontal asymptote can be found by dividing the coefficient of the x terms. So our horizontal asymptote is at y equals 2 over 1, or y equals 2. Whenever you have a rational function, the horizontal asymptote can be found by dividing the coefficients of the x values, x terms, as long as the degrees are the same. You with us, Ben? Which they are. So we can put those on our graph. The line x equals 4 is our vertical asymptote. The line y equals 2 is the horizontal asymptote. Excuse me. We can find the intercepts. Our x-intercept is where y equals 0. And as we saw, a rational function equals 0 when the numerator equals 0. We want to know where that rational function equals 0. That's where y is 0. And a rational function equals 0 when the numerator equals 0. So that'll be where 2x equals negative 2 and x equals negative 1. So that is the point negative 1 comma 0. That's the x-intercept. The y-intercept is where x equals 0. So y equals 2 times 0 plus 2 over 0 minus 4. 2 times 0 is 0 plus 2. 0 minus 4 is negative 4, so that gives us negative a half. Point 0, comma, negative a half. So that's right there. Like we've seen, all these rational functions have two parts to the graph. One part was normally in the bottom left, and by finding those two intercepts, that confirms that part. The other part should be in the top right, if it's consistent with the other ones that we've looked at. And we can confirm that by, let's say, choosing a value of x that would put us to the right of the asymptote. For example, what happens when x equals 5? What is f at 5? So it'll be 2 times 5, which is 10 plus 2 over 5 minus 1. So that'll be 12 over 1, or 12. So we have the point 5 comma 12. So again, that confirms that the other arm of this graph is in that top right quadrant. We could find, say, one other value. What happens when, let's say, x equals 10? Let's find f at 10 as well. So when x is 10, 2 times 10 is 20, plus 2 is 22. Divided by 10 minus 4 is 6. So that will be 2 and 4/6, or 2 and 2/3. The point 10 comma 2 and 2/3, so just above the asymptote of y equals 2. So there's that graph. Something like that. The domain of this would be all values of x such that x cannot equal 4. Otherwise, all real numbers. And the range, all values of y such that y cannot equal positive 2. Again, the asymptotes are key to the domain and range. Okay? So we've done different examples where we're doing transformations of 1 over x. On the next page, though, we're doing now transformations of 1 over x squared. Still a rational function, but we're starting with a different base graph. So we've got 3 different equations. The base graph is one of them, 1 over x squared. Then we have g at x as well as h at x. So we're asked to graph f and g and then f and h and compare them. So what does the graph of 1 over x squared look like? Well, the difference between this and 1 over x is that with 1 over x, when you had negative values of x, you got a negative value of y. 1 over a negative number is a negative number. However, for this one, when x is negative, when you square it, it's positive. So in this case here, the values of y will never be negative. No matter what you put in for x, if it's a negative to begin with, when you square it, it becomes positive. And 1 over a positive number is a positive. The denominator will always be positive. Let's use our graphing calculator to help us see what this graph looks like. We just said that y will always be positive, but when you put the equation in and graph it, that's what it looks like, because the value of y will always be positive. In this case, the x-axis is an asymptote, and the reason for that is because y can never equal 0. If we take the equation 1 over x squared, no matter what you put in for x, 1 over x squared will always be some value. It'll never be 0. It'll always be a number. It could be a decimal, but it's always going to be greater than 0, never equal to 0. So that is why the x-axis is an asymptote. And the y-axis is our asymptote because x equals 0 is a non-permissive value. Our vertical asymptote always comes from the non-permissive value, and that is x equals 0 in this case. So for y equals x squared, it has the x-axis and the y-axis as an asymptote. And we saw from our calculator what the graph looks like. Something like this. And once again, if you want to, you can definitely use a table of values to find a few points to draw an even more accurate sketch, but maybe I'll try and do a better job of these because they're not very good. Okay, so that's the graph of f at x. Now, for g at x, let's see if we can do some work compared to 1 over x squared. So the first thing you should notice is that the numerator went from 1 to 3. So it's like it was multiplied by 3, which would tell us we have an a value of 3. The graph is vertically stretched by a factor of 3. So that's the first thing we can say about g at x. But the other thing we can do is factor the bottom. The factor of the bottom would be x minus 5 all squared. X minus 5, x minus 5. So based on that, then we can say two things. As I said already, compared to f at x, g is vertically stretched by a factor of 3. A equals 3, so we have a vertical stretch by 3. But then on the bottom, and again we're comparing to 1 over x squared, x is replaced with an x minus 5. So this tells us we have an h value of 5. The graph will shift 5 to the right. So that's going to shift the vertical asymptote 5 units to the right. So the vertical asymptote will be at x equals 5. The horizontal asymptote is still the x-axis, because no matter what you put in for x in that equation, y will never equal 0. And y equals 0 is the equation of the x-axis. The result of vertically stretching by a factor of 3 just means that the values of y will get larger, actually in this case smaller, faster, because of your denominator, right? It's x minus 5 all squared. And then you're going to divide, actually I said it's larger to begin with, and that is correct, because now you're dividing 3 by numbers instead of dividing 1 by numbers. So all it'll do is it'll just make it get a steeper a little faster. Whoops. So it's going to look something like that. So we're asked to compare these graphs. So let's do this with a chart below here. Let's have our MPVs, our non-permissive values. We'll have our domain. We'll have our range. We'll have our vertical asymptote and our horizontal asymptote. And we'll start with the original equation, y equals f at x, which was our 1 over x squared. And the non-permissive value for that was that x cannot equal 0, and also y cannot equal 0. And those come directly from our asymptotes. Our vertical asymptote is the line x equals 0. Our horizontal asymptote was the line y equals 0. And so our domain and ranges come directly from our asymptotes or our non-permissive values. Our domain was all values of x such that x cannot equal 0, but all other real numbers. And our range was all values of y such that y cannot equal 0. So that's for f at x. That's 1 over x squared. What about g at x? That was 3 over x minus 5 all squared. So our non-permissive values here were that x cannot equal 5, but y still could not equal 0. And again, that leads us directly to our domain and range. And our vertical asymptote is now the line x equals 5. Again, they're equations of lines, so they have to have a variable and they have to have an equal sign. Okay, so now we want to compare f at x and h at x. So for f at x, we've already done it once, so we can do that again. So this is the graph of f at x. So now we need to look at h at x. And this one actually is expressed in a form that we're used to looking at with respect to transformations. If I rewrite h at x, that negative in front could be the same thing as negative 1 over x plus 4 all squared. And then the 6 that was in front is a positive 6. We're used to seeing that written at the end, though. So now it is in the form of transformations that we're used to seeing. You've got an a value of negative 1. So that's going to reflect the graph over the x-axis. You've got the fact that x is replaced with x plus 4, which means you have an h value of negative 4. The graph's going to go 4 to the left. And then a k value of plus 6, so the graph will shift up 6 units. So in this case here again, a is negative 1, which means it's going to reflect over the x-axis. And then we have h equaling negative 4 and k equaling positive 6. So the graph will shift 4 left and 6 up. Which means our asymptotes are going to change. The graph is going to shift compared to 1 over x squared. It's going to shift 4 left and up 6. So our asymptotes are going to change. They're going to go to 4 left and up 6. And also, because the graph was reflected over the x-axis, this one's going to go downwards instead of upwards. Try that again. And if you're not sure about that, use your graphing calculator. Put that equation into the graphing calculator to make sure the graph looks correct. So using the original equation, it'll be 6 take away. I'm going to open up a bracket to keep the rational expression together. 1 divided by the denominator, I need to put in brackets as well to keep it together. X plus 4, close the bracket, square it, and then close the bracket on the rational expression. Graph it. Looks correct. So now if we want to state all these characteristics for y equals h at x, the graph went 4 to the left, so our vertical asymptote was at x equals -4. That's our restriction, our non-permissive value. And it went up 6 units, so y cannot equal 6. That's our restriction on y. The domain comes from the restriction on x. And the range comes from the restriction on y. And our domain and range come directly, or I'm sorry, our vertical and horizontal asymptotes come from those as well. Our vertical asymptote is the line x equals 4. Our horizontal asymptote is the line y equals 6. Right? So these ones here, once again, we're comparing these graphs and talking about the characteristics. We're starting with f at x equals 1 over x squared. So we've already seen what that one looks like. On the desk is fine, thank you. And then for g at x, you've got -1 over x minus 3 all squared. So for that one, you have an a value of -1, which means it's going to reflect over the x-axis. And then x is replaced with x minus 3, so that's an h value of 3. So the graph is going to shift right 3 units. Shift 3 to the right. Which is going to change that vertical asymptote. It'll now be at x equals 3. Doesn't change the horizontal asymptote, the x-axis. But also because it's reflected over the x-axis, this graph will go downwards instead of upwards. So there's the new graph. And once again, if we talk about the characteristics and non-permissive values, the domain, the range, as well as our asymptotes, vertical asymptote and horizontal asymptote. So non-permissive values for the original ones are both x and y cannot equal 0. And that's where our domain and range come from. Our vertical asymptote is the line x equals 0. It's an equation, so it's got to have a variable and an equal sign. And our horizontal is y can't equal 0. Now, for y equals g at x, here the restriction on x is that it can't equal 3. And y can't equal 0. And so now we're going to compare f at x and h at x. So again, for h at x, we will rewrite that in a different form. So that 5 over top will stay the same, but that tells us that a is 5. It's the same as multiplying 1 over x squared by 5 over 1, an a value of 5. The bottom can be factored to x plus 1 all squared. And then that positive 2, which was at the start, we'd move to the end because that's where we're used to seeing it. So now we can see again, we have an a value of 5, so that is a vertical stretch by 5. This means the values of y are going to get bigger faster. And then we have an h value of -1, a k value of +2. So the graph will shift one left and 2 up, which will change both of our asymptotes. But first we'll start with the original one, 1 over x squared. And now we'll do our new one, which goes left 1. So our vertical asymptote will go to the left 1, up 2. So our horizontal asymptote will go up 2, as well as vertically stretched by a factor of 5. So it's just going to get steeper a little quicker. So for y equals h at x, our restrictions are x cannot equal -1, y cannot equal +2, so the domain is all values of x such that x cannot equal -1. And there's the equations of our asymptotes. Okay. So we should do questions 2 and 4 on page 442. I will post those solutions to Google Classroom so you can check your answers. So I think we just have one more lesson left, 9.2. Which we'll do all in one day tomorrow. So Wednesday, you can count on a quiz on Chapter 9. Okay? Quiz on Chapter 9 on Wednesday, and then Thursday we'll go through it. And then after Christmas, it'll be chapters 10 and 11 to finish off.
Do we have a class on Thursday? Is the time show?
We don't know what the schedule is going to be yet. Whether it's going to be a shortened block where we have all the blocks, or if just the afternoon classes are canceled. It's on a need-to-know basis, apparently. Okay, so those questions on page 442.